Okay, so hello everyone, welcome to the video number 3 of our tutorial on the use of ANSYS for analysis of analysis of electrical devices. And in this video we going to transit to the high frequency simulation of antennas. So in a broad sense, an antenna is a device that converts the waveguiding modes or localized modes of electromagnetic field into freely propagating fields, or vice versa. In the receiving mode, antenna transforms the freely propagating modes into the waveguiding modes. And more specifically, we were going to design the device so-called microstrip patch antenna, and this is an important type of an antenna widely used today, especially in smartphones, right? So, and in different Wi-Fi systems, basically for consumer electronics. So let's transit to design a patch antenna, and we're gonna design it to the frequency around 2.4, 2.5 in this video. All right, so in order to design an antenna, okay, we create a project. All right, let's give it a name, maybe patch antenna. Okay, and I save this project. So to design an antenna, we use a high frequency solver. Okay, so I'm gonna go and choose this one now. High frequency simulator. Okay, and the first step is to go to solution setup and double check that it is HFSS. And I'm gonna change this and double check that we got the model option for the solver. So I choose model and click OK. Save. So as usual, I start with drawing the structure, and our structure will be we'll get a ground plane, then a substrate, and a microstrip on the other side. Okay, so it's a structure like this. So let me start with drawing a rectangle first in the XY plane, and I rename this structure to the ground. Okay, so it's going to be ground, and I give it a color. So the ground is typically made of copper or metal, something like that. So I change the color to this orange-ish color, apply. Okay, so next I give it the geometrical parameters for the x size of the ground plane, and it's gonna be the size of our structure. So I just put maybe Lx for the x size, and let's put something like 60 for now, 60 millimeters. Okay, and the same for Ly. It's gonna be also 60 millimeters. Okay, and the position in 0 axis is going to be 0, and y is going to be Lx over 2 minus Lx over 2, and y minus Ly over 2, apply. Okay, so it's gonna be perfect quadratic shaped rectangle, looking like this. So next we create the substrate. Okay, the substrate is going to be a dielectric. So I need to draw the three-dimensional box. Okay, I draw the same section here and give it some height. Okay, and change the name of the box to the substrate. Give it some color and geometrical parameters. So for the y and x is going to be the same size as the ground. It's going to be lx. This one is a y. This one is lx. And the z size is going to be the thickness of the substrate. Let's parameterize it by the letter d for the thickness and give it maybe something like 1.6 millimeter. This is typical number for the PCB boards for these applications. Okay. The position also minus L x over 2 minus L y over 2 and 0, because the ground doesn't have any thickness, so it's still 0 for the position along the axis z. Okay. So this is our ground and the substrate, and now I need to draw the patch. So the patch is another metallic rectangle on top of this on top of the substrate. So I draw another rectangle, arbitrary for now, give it a name patch. Okay. Give it a name patch. Also change the color to like copper one, and now I give the geometrical parameters. So I want to parameterize the size of the patch, so I give a name to the x size, LPX, standing for length patch x, right? And let's give it some number like 30 millimeters. So these numbers for now is just arbitrary, and ly lpy is gonna be, for example, 40. I want to make it a rectangle, 40 millimeters. Oops, position. Right, so for the position, in z direction is gonna be thickness of the substrate, so I put d here, and for the x it's gonna be minus L patch x over 2. For the y it's gonna be minus L patch y over 2, and it's gonna be working just perfect. Okay, so here is a patch over a like PCB board. Okay, like with metallic copper. It doesn't get any material now, but it's gonna be like a copper or perfect metal here in the bottom, and then the substrate will be made of some dielectric. All right, so this patch gonna be used as a antenna. Okay, so we need to get a port, a drive, right? So the port will be connected to the a line called microstrip. So I need to draw a microstrip now, and this microstrip will go along this upper surface of the of the substrate right to this edge along the axis. What is this? Axis X over here. So it's useful to now change the reference coordinate system and create a new one, a local one, somewhere. I mean, in this point. So we will count all the size and position of the microstrip according to this point. It's gonna be more useful, right? So I create a new one and put it somewhere here. Okay, so it's a new coordinate system. Now if I go to this coordinate systems, I can find this new one over here. So we have this global coordinate system, which is always in the origin of our area, right? And the new one, relative coordinate system one, that we just created. And I can, of course, I can change position of this one. I can change the name of it, but let's leave it unchanged for now. I can change the origin. So first of all, let's change the origin to along the Z. So this origin is referred to the global coordinate system. Okay, I can change that, but for now I have only one other coordinate system rather than this new one, which is global. So I refer all my points to this global coordinate system. So in the global coordinate system, the origin of the Z coordinate of the origin of this coordinate system going to be D, right, for the thickness of the substrate, and the X gonna be what? It's gonna be L. It's gonna be L X over 2 millimeters, of course, and okay. And this to denote the orientation of the axis. Okay, so let us maybe leave it like this. Okay, so this is a new coordinate system, and if I will change the dimensions of my antenna, it will find a new position. It's gonna be tied to this point over here. So now I'm ready to draw the microstrip. Okay, so I just draw microstrip like this. I go to the first of all, I give it a name. Strip. It's gonna be also copper-like metal. Okay. So now change the the size of it and dimensions. And so now by default it's changed to the new coordinate system. Okay. New coordinate system, and let's give it a X size to L. Let's make it up to the center, so it's gonna be L X over 2. Apply. And Y size, let's make it L. So it's going to be the thickness of this microstrip. Okay, so for now let's parameterize it by L I'll strip y, and the typical size of this is something like 3 millimeters. Okay, something like this. Now I need to change the position, so the position of this microstrip in the new coordinate system is going to be minus lx over 2, right, yes, and the position over the y is going to be minus l strip over y over 2. Okay, and z gonna be 0, because now we are in the new coordinate system. Okay, so let's double check that. Yes, it's indeed drawn over the upper plane. Okay, so this is our microstrip. So if we connect this, so if we use this microstrip patch as an antenna, it definitely won't be matched to the generator or to the source. So we will normalize the characteristic wave impedance of this microstrip to 50 ohm, which is the typical number for coaxial cables and for outputs of generators, etc. So it's going to be 50 ohm here, but this patch definitely gets another input impedance. Okay, so we need to match the two characteristic impedance to the input impedance of the patch. And in practice, it is done via the cuts along this patch, along this microstrip here and here. So let us make this cuts. Okay, so to do so, I draw another. So before that, it's instructive to create another coordinate system in this point over here. Okay, this point over here. So I create a new coordinate system, and I check that if I refer the new one to the previous one, okay, the origin is in the z0, y divide 0 for the y, it's gonna be 0 anyways, and and for the x, it's gonna be minus lx, it's gonna be lx over it's gonna be lpx over 2. All right. Okay, so it's a new coordinate system located exactly at this point, at the boundary between the microstrip and the patch. All right, so now I draw the new rectangle over here, something like this. with the sizes. So let's name it cut. The color doesn't matter, but what matters is this the cuts over here and here on both sides from the microstrip. Okay, so it's gonna be wider than the size of the width of the microstrip. Let's parameterize the X size, for example, L cut X, and let's give it a size maybe 10 millimeters for now. Not good. So it's gonna be, maybe we'll change that. And Y size, L cut Y, also 10 millimeters. Let's check what we got. Okay, and next let's make this one to be equal to minus L cut X over 2, and this one is minus L cut Y over Y over 2, and 0 because we are in the new coordinate system. Apply. Is it any good? No, let's make this is it X? So let me make this unequal, like, yeah. Or maybe give it just a little bit more, so it is not exactly at the boundary. Okay, something like this. So here are the parameters for the cut, and I click I guess okay, and now we change the Y size of this cut, for example, to something smaller. So the microstrip is 3 millimeters, so let's make this Y size of the cut to be equal, maybe something like 5 millimeters. Okay, much better. So now I can subtract the cut from the patch. So I select cut and I highlight cut and the patch, right, and go to the Boolean operators and do subtract cut from the patch. Click OK. Okay, and now I can I can unite the microstrip and patch into one single structure by clicking, selecting both of them and clicking unite. All right. So here is the geometry for our microstrip antenna, microstrip patch antenna, and these cuts are parameterized, so I can change the cuts by changing this L cut Y. For example, I can get, for example, or yeah, so by changing this L cut X, I can change the length of the cuts. For example, for 2 millimeters, I have very small cuts, but If I change it, for example, to 9, I get longer cuts. 12, I get even longer. So what these cuts affect? They basically work as the transformer of an impedance from the characteristic wave impedance of microstrip to the input impedance of the patch. Okay, so it is a transformer. All right, so this is the structure of my antenna, but it's made of nothing for now, right? I need to give it a material. In ANSYS HFSS, I cannot assign a material to the rectangle, right? A structure without any thickness, with the zero thickness. I cannot give it a material. So I must consider the rectangles as a perfect electric conductor. So basically a perfect metal. And this is a good approximation in the high frequency case, for example, in this gigahertz frequency range, because the field virtually doesn't penetrate inside the metal. In reality, it penetrates by a factor of maybe several hundreds of nanometers, but comparing to the actual size of the structure, which can be hundreds of micrometers, is nothing. So virtually the field doesn't penetrate inside the metal, so we can use them as a perfect electric conductor. So in order to make this patch as a perfect electric conductor, I highlight the structure and then go to assign boundary and select perfect electric conductor. Click OK. All right, and double check that it appears in the boundaries in the project structure, right? So I do the same for the ground. Okay, I highlight the ground and then do assignment boundary perfect electric conductor 2. All right, so the ground and the patch now are both made of perfect electric conductor. So next I need to excite this antenna made of perfect electric conductor already. So I will use the discrete port, lamp port excitation, lamp port element, and this lamp port element must be assigned to another rectangle over here. So in reality, we excite this antenna through between this ground and microstrip, so we can connect or solder something like a semi connector, and it will be working as a port. But in simulation, we need to draw another rectangle over here. So for now, I am in the XY plane. I need to change it to a ZY plane and draw something like this in this plane, right? So this is the rectangle. I can change the parameters of this rectangle. I go to the geometrical parameters. I change the coordinate system to the first one, so which is the coordinate system located over here at the edge between the microstrip and the substrate, right over here in the center. So it's gonna be like this. And so for the Z size, I make it D, right? Then for the X size, for the X size, I do L strip Y size. I do a microstrip Y. Right. Then here I do minus. So it's gonna be I'll strip x over 2 maybe. This one gonna be maybe 0 and 0. Let me check. Oops. Y strip. Oops. This one gonna be 0. I believe, and this one is minus strip over the y over 2. Okay. Almost right, but maybe size minus d because the orientation of yeah. So here is the geometrical parameters for this rectangle that will be used as a excitation port, and I do okay. So this is the excitation port rectangle. So next I can choose this. Well, first of all, I can rename it to the port. Color doesn't matter, and so I highlight this or choose this port and then do assign excitation and then port and then lumped port element. Okay, so we see that the ANSYS will consider this port as a 50 ohm port, which is the wave impedance of a conventional coaxial cable. So I do next, and now I need to draw an integration line. So I choose a new line, and I need to draw a new line in this across this ground and microstrip. Right. So I draw a line like in the center. I do next and I believe finish. Okay, so now I can change. I can check that I have the excitation. This in the project manager. Okay, and this discrete port excitation is appears as a structure like this. All right, so I've got my excitation, I've got my antenna and substrate. What else? I need to create the simulation area around. Right, so let me change it back to yeah. So now I need to create the area around. To do so, I create the region. I create the region with the percentage value of 50% all around, and this is the percent from the structure size. Okay, and when I click OK, I get the volume, but I don't like this volume because the height is too small. So now I can go to the height parameters and change the parameters for the z direction from 50 to maybe 500. Let me check. Let me try. 500 is enough as I believe. All right, so the structure is all surrounded by this simulation area, and this simulation area must be assigned the boundary, radiation boundary, right? So this is the boundary that works as a perfectly matched layer. So it's considered, so it's a layer that continues the radiation field to the far field so it basically works as an open boundary, right? So in fact it absorbs perfectly the fields at the boundary, so it doesn't create any back reflections from the area back to the antenna, so you have no reflection. At the same time, it records all the fields at the boundary, and it can construct the fields in the far field. All right, anyway, so we create this radiation boundary. Okay, and yeah, so basically we have the antenna radiation boundary, and we ready to before proceeding to the setting analysis, we need to change the material of the substrate, right? Because for now it is just vacuum and it's not realistic. We need to change this material to some epoxy materials. Epoxy, this one, FR4 epoxy material. So it's just dielectric that at gigahertz frequency range has relative permittivity of 4.4, no magnetic permeability, and considered to have no conductivity in bulk and small loss tangent, so it's a pretty effective material for PCB boards. Okay, so I click OK. So now my material is made of this epoxy FR4 material. Right. So now I'm ready to proceed to setting the analysis. Okay, I create analysis, go to advanced. I want to simulate my structure in broadband from maybe 1 gigahertz up to maybe like 4 gigahertz. Okay, so I include this important case of 2.4 gigahertz in this domain. I also can change the maximum number of passes, so I ensure that the project converges to the desired accuracy. And what else? That's pretty much okay. I mean, we can improve the accuracy over here, but for such a project, it's not really necessary. I can do okay. And here, for the frequency sweep, I have starting 1 giga, ending 4 giga. So the sweep type, let's change to fast. Okay, double check that we have safe fields selected, and then okay. All right, so we have project, we have boundaries, we have basically all set, and now we can evaluate we can validate first the project. So all these check marks are green, and we can go and and simulate our antenna. So for now we get these cuts of the length of what it was 5 millimeters. So let's simulate our antenna with these particular cuts. So my project has been executed well. It took maybe 2 minutes to simulate it on my computer. So first of all, so let me tell you a few words about the most important parameters of any antenna, and in particular this patch antenna. So it basically gets two main parameters, right? The first one is how the antenna transforms the waveguiding mode to the free space radiation, and it's characterized by S11 parameter or reflection parameter. And this parameter characterizes the antenna, the transformative properties of this of the antenna, right? So we can go to the results, create the result rectangular plot, and here you see by default we have this S11 parameter. Double check that we have this parameter frequency. Create new report. Okay, so we've got this response of our antenna. So as we can see, the antenna in this frequency range, it gets two resonances or two resonant dips in the S11 response. We can add a marker to see what is the frequency here. So it's a 2.26 and here 3.49. So this is just a response of an antenna with the selected particular parameters. This fundamental resonance of the antenna gets the S11 parameter of minus 10 dB, which is not that high. In fact, in practice, we need something better than minus 10. So maybe minus 20 dB is better, because the higher this negative number in dB, right, the closer this result to zero in linear scale, right? So if I create the same but in the magnitude, in the linear scale, I will see that my antenna, in terms of amplitudes of the field, radiates 70% of the field, right? And if you square this number, it will be some number in power. So it's still 70% of the field, and I need it works okay, but not perfect. First, and second, this dip is located somewhere where it was at 2.26 gigahertz. Typically, we design such an antenna to a frequency around 2.4, for example. So we need to design this antenna, right? And in order to design the antenna, the best way would be to go to the optimetrics and add the parametric sweep to the antenna. So we will do that in a second. So S11 is the first important parameter of any antenna, because it characterizes how antenna transforms the field, the wave propagating field, the waveguide propagating, to free space mode. So basically, the smaller this number at resonance, the smaller the return loss. Okay. And another important parameter is the radiation pattern, basically how antenna radiates in terms of radiation density in space, in different directions. So sometimes we need unidirectional antennas. For example, when I spread the Wi-Fi signal, like internet signal in my home, I need to spread it around like in all directions, almost equivalent, right, in the same time. So sometimes this parameter needs to be designed to, like, the smaller the better, to make the antenna unidirectional, omnidirectional. But sometimes I need a very high directivity. For example, for communications from link to link, I need to achieve the larger the better the directivity, in order to reduce the diffraction loss. Okay, so I need to concentrate all the energy, all the information in a single very narrow beam of radiation. And of course, it's not possible to achieve infinite directivity, but the larger the better for communication purposes. So in order to calculate and see the radiation pattern of an antenna, I need to go to radiation in the project manager and first create the integration sphere, infinite sphere over here. Okay, so we create this infinite sphere, I click OK, and it's created. And now I can go to results and create far field results report. And let us do three-dimensional polar plot. Okay, three-dimensional polar plot. And then I, for example, can see the directivity over here. Directivity total. I create new report and see the directivity pattern of my antenna. So as expected, the antenna doesn't radiate towards to the ground plane, of course, because it's a perfect conductor, and the most of the energy radiates as a pretty much like a narrow lobe to the upper direction. Yeah, so in order to be able to see that, so anyways, so this is the radiation pattern, directivity pattern of my antenna. But antenna, as we discussed, antenna is not tailored to the frequency of interest, which is 2.4 gigahertz. And in order to design an antenna to the desired frequency of interest and maybe improve the S11 parameters, I do parametric sweep. Okay, so I create the parametric sweep. And what I change, let me double check what I changed to change the cut. So I change the L cut X, right, from something like 2 whatever number it is. Okay, L cut X, L cut X. Okay, so let's go to the optometrics, create the new parameter sweep, linear sweep, L cut X from, let's do maybe from 2 millimeters to maybe 15 millimeters with a step of maybe, let's do maybe 2 millimeters. Okay, so is it good? Probably stop 16 millimeters. Add, okay, and at this point also we can change the mesh parameters, right? So initial mesh settings, let's put something like this is good, but probably improving mesh over the patch would be a good idea. So highlight patch, do assign mesh operation, on selection, lines based, and let's do maybe 5 millimeters for the maximum element length. Okay, and I can also always see the mesh by by clicking plot mesh. Done. Okay, and it's gonna be visualized when the simulation is done. All right. So now I have the mesh settings. I can also add the initial mesh settings and the mesh inside the box. Inside selection, length based, maybe something like 15 millimeters. Okay. And okay, so now I can go to Optimetrics and analyze the parameter sweep. Let me put on pause the video. All right, my project has been executed. It took some time, maybe 5 or 7 minutes, because it was parametric sweep for seven parameters for the length of the cuts. Okay, and now we can see how the length of these cuts affect the S parameters of the antenna. Okay, so I go to the results, select frequency here, sweep, S41 parameters, create a new parameter report. Okay, so now I can see that in contrast to the previous parameter, which was maybe this one, right? For the S11 minus 10 dB. So now the best case, right, the optimized case gets almost 20 minus 25 dB, which is much better, meaning that the return loss is in really small. And the frequency, the operation frequency is 2.3 gigahertz. Is still a little bit off the desired frequency of 2.4, which is somewhere over here, but the antenna operates much better at the frequency 2.3 now. So as we can see, if we start from very short 2 millimeter cuts, right, we get something like this, and the returning loss or the S11 parameter is around minus 10, then it gets more better. Finally, at 8 millimeters, it's the best, and then drops down again to a very small number for a very long parameter. So this way we optimize the length of the cuts, and it is 8 millimeters. So now we can also plot the same in the linear scale to see what is the actual returning loss. Okay, so the returning loss in the in terms of field is very small. It's less than, it's about 95% efficiency, so only 0.05% is lost. And if you square this number, you get the returning power loss, and it's going to be even smaller. So the antenna operates, the optimized one operates a little bit much better. And in order to, so as you can see, when we change the length of the cut, the maximum, the minimum point also shifts, right? It also changes, but not in the, I mean, not very much. In order to change this point, this frequency, one can change the size, the dimension of the patch, yeah, basically dimension of the patch or the width of the cuts, but typically we change the width of the patch. Also, we can see the distribution of the mesh all over our structure, right? And as in other projects, we can also see the electric and magnetic fields distributed over the elements of the antenna. For example, if I want to see the electric field distribution over the patch, I can go to the vector distribution of the field, highlight it, and see nicely the electric field distribution. So by default, since this field in the cuts is like strongly localized, we need to change these numbers for the minimum value and for the maximum value before 2000 or even maybe 1000 or even maybe 100. Right, to be able to see the actual field, the distribution all over the patch. The same way we can see the magnitude, the distribution of the magnitude of the field. I, by the way, can change the frequency, right? So all over the selected frequencies, I am interested, for example, in the frequency 2.3 gigahertz. 2.3 is over here. To do so, I just change the solution from setup last adaptive to sweep. Okay, done. And why I don't see any fields? The magnitude is not active for some reason. Okay, here is the field. I can do animation of this in view, animate, magnitude. Okay, so we can see the animation of the field, how the field distributed over the patch, and show up the directivity distribution of radiation of our antenna at different frequencies. So this is basically end of this video on tutorial of simulating the patch antennas. So in this video we learn what is the antenna, what's the main parameters of an antenna, and how to simulate a patch antenna using ANSYS HFSS. Thank you very much.